Hello, my name is John Cody. I'm an engineer from Vancouver, Canada. Today I'll be talking about universal hyperbolic geometry and alternate forms for the quadria of a projective quadrangle. So in a previous video I explained what the quadria of a projective quadrangle was, what the formulas were in universal hyperbolic geometry, and in this video I'll provide some alternate forms for those formulas. So in universal hyperbolic geometry, we are using the point of view that geometry is really about formulas, and we're building a library of useful formulas. It is a metrical algebraic geometry. So it is geometry looked at algebraically with a metrical structure, typically involving a quadratic form. With a metrical approach, we are interested in making measurements and making computations. There's a flexibility in the metrical structure. We can have a Euclidean quadratic form or a relativistic quadratic form. In universal hyperbolic geometry, metrical objects are invariant quantities, and they are the building blocks for other invariant quantities. In universal hyperbolic geometry, metrical quantities such as the quadrants between points and the spread between lines are projectively invariant and are used in formulas of other projectively invariant quantities such as the quadria of a projective triangle or the quadria of a projective quadrangle. Okay, so in this subject, it is divided. The subject of geometry is really divided into two halves. There is an affine geometry and a projective geometry. These are like two sides of the same coin. And for affine geometry, we have a formulation of it called rational trigonometry. And in projective geometry, there's a formulation called universal hyperbolic geometry and spherical or elliptic geometry. So in this subject, in these two halves of the subject, under affine geometry or rational trigonometry, we have these quantities of interest and these formulas of interest. And there are existing formulas that have been previously derived for these quantities in both affine geometry and projective geometry. So there are formulas for the quadrants between points, the spread between lines, the main laws in the subject. There are 5 main laws in affine geometry, which are Pythagoras' theorem, the triple quad formula, the spread law, the cross law, and the triple spread formula. And in projective geometries, the main laws are Pythagoras' theorem, the triple quad formula, the spread law, and the cross law. And the metrical quantities are quadrants and spread, and the quadria, the notion of quadria, it's a quadria of a triangle is similar to an area of a triangle in affine geometry, and there's a metrical quantity called the quadria of a triangle in projective geometry, and its dual, the quadrille of a trilateral. So in projective geometry, there's a duality between, in 2D projective geometry, there's a duality between points and lines. So we have these two invariant quantities. The quadria of a triangle is the most important invariant quantity in projective geometry, and its dual is the quadrille of the trilateral. Similarly, in affine geometry, we have a quantity called the quadria of a quadrilateral. So we have an existing formula for that. And in projective geometry, we have the quadria of a quadrangle and the quadrille of a quadrilateral. These are duals of each other. I'll provide a reference to video explaining what the main laws are in both affine rational trigonometry, affine geometry, and projective geometry. So you'll see the link right here. So the main references for the subject are For rational trigonometry, the main reference is the book Divine Proportions, Rational Trigonometry to Universal Geometry. For projective geometry, the main reference is this paper, Universal Hyperbolic Geometry 1 Trigonometry by Norman Wildberger. And the main reference for both of these subjects is this YouTube channel, Insights into Mathematics, given at this address right here. I'll provide links at the end of the video to these. And Universal Hyperbolic, there's a video for Universal Hyperbolic Geometry, the quadria of a projective quadrangle. And here is the YouTube video link for that. So, and they also have a couple of links for the quadria of a quadrilateral under affine geometry. So in this YouTube channel, Insights into Mathematics, the main references are the video Math Foundations 127A and Math Foundations 127B, which is entitled The Cyclic Quadrilateral Quadrea Theorem. And the video Math Foundations 132, the Brett-Schneider-von Stout formula for the quadria of a quadrilateral. Okay, so we'll be talking about the quadria of a quadrangle in this video, an alternate form for that. So here we have a quadrangle with projective points A1, A2, A3, and A4. The quadrants between projective points A1 and A2 is Q1. The quadrants between projective points A2 and A3 is Q2. The quadrants between projective points A3 and A4 is Q3. And the quadrants between projective points A4 and A1 is Q4. And the spreads at point A1, A2, A3, and A4 are S1, S2, S3, and S4, and those are the four spreads of the quadrangle. And here we have a triangulation where we have a chord going from A1 to A3 with quadrants of Q5, and the quadrants and over on the right-hand side here is an alternate triangulation of the quadrangle A1, A2, A3, A4, with a chord going from projective point A2 to A4, and which has a quadrant Q6. Okay, so what we're going to do now is find an alternate form for the quadria of a projective quadrangle. And we're going to start off by using the spread law, which was one of the main laws in Universal Hyperbolic Geometry. So here again we have the quadrangle with projective points A1, A2, A3, and A4, and we've drawn the two chords here, and they intersect at a point A5. So we have some new spreads and new quadrants to talk about. So at point, when you put these chords in here, it created some new spreads, which are R1, T1 at projective point A1, R2 and T2 at projective point A2, R3 and T3 at projective point A3, and R4 and T4 at projective point A4. And there's four new quadrants. The quadrants from A1, projective point A1 to A5 is P1. The quadrants from projective point A2 to A5 is P2. The quadrants between projective point A3 and A5 is P3. And the quadrants between projective point A4 and A5 is P4. And the spread between the two chords is S. Okay, so with using the spread law, here are the formulas for the spread law applied to the four different triangles in this triangulation. So we have for triangle A1, A2, A5, the spread law is given here. We have Q1 over S, the spread between the chords, is P2 over T1. There's P2, the quadrant's P2 over spread T1, and that's equal to the quadrant's P1 over R2. The second line set of equations here, or equalities, is for this projective triangle A2, A3, A5, and the spread law says that Q2 over S is equal to P2 over R3, and that's equal to P3 divided by T2. And similarly for the other two triangles, we have triangle A3, A4, A5, we have Q3 over S. Q3 divided by S is equal to P3 divided by R4, and that's equal to P4 divided by T3. That's these equations here. And finally, for projective triangle A4, A1, A5, we have Q4 over the spread S is equal to P4 divided by R1, and that's equal to P1 divided by T4. Okay, so in a previous video I presented this equation here for the quadria of a projective quadrangle. The quantity A is the quadria of the projective quadrangle, and these quadrants is, and it's an equation of quadrants and spreads. And what we're going to do is substitute this term here, Q1 times Q2 times Q3 times Q4, with an alternate form. So from the spread law, when we bring the S for each of these equations here, when we bring S up, we have Q1 is equal to P2 times S divided by T1, and that's equal to P1 times S divided by R2. And similarly with the other equations, Q2, when we bring the S up onto the other side, it's P2 times S over R3, and that's equal to P3 times S over T2. Okay, so when we do that for all four of these sets of equations, then when we multiply Q1 times Q2 times Q3 times Q4, we get S to the power 4 times P1 times P2 times P3 times P4 divided by R1 times R2 times R3 times R4. And that's also equal, we also can get S to the power 4 times P1 times P2 times P3 times P4, all divided by T1 times T2 times T3 times T4. And here's another alternate form of that by combining different combinations here. We have Q1 times Q2 times Q3 times Q4 is equal to S to the power 4 times P2 squared, all squared, divided by T1 times R3 times P4 squared times R1 times T3. Again, just by using different values in these equalities. And lastly, we have Q1, Q2, Q3, Q4. When we multiply all these together and we choose the terms with P1s in them, P1 here and P1 there, we get S to the power 4 times P1 squared divided by T2 times R4 times P3 squared divided by R2 times T4. So these are alternate versions of Q1, Q2, Q3, Q4. So, and next we're going to multiply the quantity Q1, Q2, Q3, Q4 by a clever choice of 1. And that clever choice of 1 is 4 times 1 minus S1 times 4 times 1 minus S3, all divided by 4 times 1 minus S1 times 4 times 1 minus S3. So this value on the right hand side is equal to 1. So we get when we do that, we get Q1, Q2, Q3, Q4 times this version of it. We get is equal to S to the power 4 times P2 squared times P4 squared divided by 4 times T1 R1, we have T1 and R1 here, times 4 times R3 T3, all divided by times this value of 1, where we brought the 4's down here, times 4 times 1 minus S1 times 4 times 1 minus S3 divided by 1 minus S1 times 1 minus S3. And that's equation 2. Next, we're going to use the alternate form of the triple quad formula. The triple quad formula was one of the main laws in universal hyperbolic geometry. And that says that a plus b minus c all squared is equal to 4 times ab times 1 minus c. And when we do that, when we apply that, we get where a is R1 and b is T1 and c is S1, or a is R3 or b is T3 and c is S3, then we would get R1 plus T1 minus S1 all squared, like on the left-hand side here, is equal to 4 times AB, that'd be 4 times R1 times T1 times 1 minus S1. And then we're going to do that again with the other term. So we have A plus B minus C, that would be R3 plus T3 minus S3 all squared, and that's equal to 4 times R3 T3 times 1 minus S3. So we're going to substitute this into equation 2. So this was the denominator over here before, that the right-hand side was our denominator in equation 2. And we're going to substitute that in, this for the denominator now. Then we get Q1 times Q2 times Q3 times Q4 is 16 times S to the power 4 times P2 squared times P4 squared times 1 minus S1 times 1 minus S3, all divided by R1 plus T1 minus S1 squared times R3 plus T3 minus S3 squared. And then lastly, we're going to substitute Q1, Q2, Q3, Q4, this right-hand side for that, into equation 1, which is our initial equation for the quadria of the projective quadrangle. So we're going to replace Q1, Q2, Q3, Q4 in equation 1 here with what we arrived at previously. So after substituting in equation 1, we get A minus Q1, Q2 times S2 minus Q3, Q4, S4 all squared is equal to 64 S to the power 4 times P2 squared times P4 squared times 1 minus S1 squared times 1 minus S3 squared, all divided by R1 plus T1 minus S1 squared divided by R3 plus T3 minus S3 squared. So we end up with something squared is equal to something squared. So the left-hand side of this all squared is equal to right-hand side all squared. And so we're going to take the square root of both sides, and we're going to get A minus Q1, Q2, S2 minus Q3 times Q4 times S4 is equal to, it could be plus or minus now, 8 times S squared times P2 times P4 times 1 minus S1 times 1 minus S3, all divided by R1 plus T1 minus S1 times R3 plus T3 minus S3. And when we substitute for the quadria, this Q1 times Q2 times S2 are quadrias of triangles, and here's an alternate form of that. Depending on the triangulation, we're going to get Q1 times Q2 times S2 is equal to Q5 times P2 times S, where S was the spread between the chords. And we also have Q3 times Q4 times S4 is equal to Q5 times P4 times S. So back up to our projective quadrangles. So we're looking at this triangulation here where we have a Q5. Okay, so there's two projective triangles here, A1, A2, A3, and the quadria of that projective triangle is Q1, Q2 times S2. And similarly, this triangle A3, A4, A1, the quadria of that projective triangle is Q3 times Q4 times S4. But with this triangulation down here, if we just had the one chord, or no, with this triangulation here, this quadria of this projective triangle A1, A2, A3 is also Q5, which is the quadrants of the chord between A1 and A3, times S times P2. So that's another formula for the quadria of this projective triangle A1, A2, A3. It's Q5 times the spread S times this quadrant's P2. And similarly for this projective triangle A1, A3, A4, the alternate equation of the quadria of that projective triangle is Q5, the quadrant's Q5 between A1 and A3, times S, the spread S times P4. So that's what we're substituting in. Those are the So that's what we were substituting here for these quantities in here, and we end up with an equation in terms of the internal quadrants and spreads. So we end up with an equation A, the quadria A of a projective quadrangle is A minus Q5 times P2 times S minus Q5 times P4 times S is equal to plus or minus 8 times S squared times P2 times P4 times 1 minus S1 times 1 minus S3, all divided by R1 plus T1 minus S1 divided by R3 plus T3 minus S3 in the denominator. And using a similar reasoning with the other triangulation, so up here we had this triangulation of the projective quadrangle with quadrants Q6 between A2 and A4, and also using similar derivation process for Q1, Q2, Q3, Q4, but we're going to use this term here, S to the 4 times P1 squared times P3 squared divided by T2 R2 T2 R4 R2 T4. And when we follow the same procedure, we end up with an equation for the other triangulation. We end up with the quadria A of the projective quadrangle minus Q6 times P1 times S minus Q6 times P3 times S is equal to plus or minus 8 times S squared times P1 times P3 times 1 minus S2 times 1 minus S4, all divided by R2 plus T2 minus S2 times R4 plus T4 minus S4. Okay, so we ended up with two equations for the quadria of a projective quadrangle. These are alternate forms of the quadria of a projective quadrangle where there are no square roots, and we're using internal quadrants, there's no Q1, Q2, Q3, Q4 in any of these two equations. Okay, thank you for listening. I will provide some links to some videos about universal hyperbolic geometry and rational trigonometry, and also other references you can find in the description of the video. Okay, thank you very much for listening.